Okay, so this is the line. And I think with Excel, you know that you can use the function of trend line to get the parameters. In this case, this is your A0 and this is your A1. And also, if you use the formulation from the textbook, you can get the same answer. Okay, so in this case, A0 is just your bar Y minus A1 X bar. So this is the same thing, which is, oops, this one. This is your average. This is your average, which is your bar X minus your A1 times, this is your bar Y. So the blue one is your bar Y, Y axis, minus A1 times your bar of your, the average of your X axis. So in this case, answer as your Excel trend line. Okay, so note that in this case, we have, oh, a little bit slow here. I stop sharing my Excel. Close my Excel. I think my PC is running out of memory. Yeah. Okay, so if you take a look at this, again, okay. Let me close my. Sorry, this always happen. I don't know what is wrong here. Okay, so it's back now. So you can see that we have 5 data points, yeah, 5 data points. And what we did was we use linear regression. We use linear regression because in this thing, it asks for 2 unknown parameters, 2 unknown parameters. So there are 4 data points. There are 5 data points, but the unknown parameters are only 2. So only 2 means A0 and A1, which should this model, which is linear regression. But the issue here, your original equation is not in this form, which is not linear. So what you need to do is to linearize the original equation. Okay, so now let's move to question number 3. Question number 3. So note there in this question, note that this is our x value, x 8, 9, 10, 8, 9, 11, and 12. So this is log 10, log base 10 of 8, 9, 11, and 12. So use data in table 2 to estimate log base 10 of 10. So what is log 10 base 10? I think you should know this is 1, right? This is 1. So what we are going to do here, instead of using regression, we are going to use interpolation. Okay, so look at these 2 tables here. Okay, table 1 and table 2. What are the natural difference between table 1 and table 2? Can anybody spot the difference? No one? Kamu ni semuanya nak kena spoon feed ni, aduhai. Pagi-pagi masih brain freeze lagi ni, tak bergerak lagi. What's the difference here? Note that in this case, we have data from experiment. And as we know, data from experiment is bound to have errors. I think I mentioned before that in UTM, the famous error is Rayleigh parallax. Saya kalau baca report mesti gelak aja lah. Every semester. Rayleigh parallax. So this is funny. So this has errors. This is errors because data from experiment, we have errors coming from sometimes from your reading, from your silly mistakes, and of course, from your equipment that you use. Okay. Now let's look at table 2 here. Table 2 here is log, which is a function, And you know, this is an analytical function, and it has no error. So if you push your calculator for log 8, it should give you the same exact number as what is shown here on the table. Am I correct? Can anybody check your calculator? I think I'm using Excel for this one. So hopefully when I'm using my calculator, it will be the same value. Okay, where is my log here? Log of 8. Okay, so, all right, so I get the same number as on my question paper. Right, so this has no error at all. This has no error at all. So should we use regression here? Should we minimize the error? There's no error. So what is there to minimize? What is there to minimize? There's no error at all. The error is 0. It is already at a minimum. Okay, so this is when you use regression. For example, in your fluid mechanics class, right? Your Reynolds number, right? Reynolds number come from a curve and it is digitized. Okay, digitized and put in a table form. So it is easier for you to use. But sometimes the value is not in the table. For example, in this case, what I want is x log 10. But unfortunately, there's no 10 here. We have 8, 9, 11, and 12. There's no 10 here. So what do I do? So I think this is very familiar with you. You will do your interpolation, right? You will do your interpolation. So in this case, use data in table 2 to estimate log 10, base 10 by means of linear interpolation. Linear interpolation means using 2 data. So I think this is the simplest of them all, which is 9 and 10. 9 and 11. And in between 9 and 11, that's a value 10, right? So let's try to do this. So let's say that okay, let me move my things here. Okay, so this is question number 3. Yeah. So this is interpolation. Interpolation. So we have x and log x. So we are assuming that of course to me log mean always log base 10 and ln natural log. That's a different kind of log. So we have 9 and 11. So 9 is why don't we use Excel in this case, or maybe we can just do it this way. Okay, so this is x, this is log x. So let's say this is 9 and this is 11, and let's assume that it is I don't know how the curve look like, but let's say it looks something like this. Okay, and we know that 10 is here. Okay, so this is the actual line. But when you use linear regression, linear interpolation, okay, linear interpolation, you can see that you use 2 points, right? You use 2 known points, which is this point and this point. So the best line that you can draw with only 2 points is a straight line, right? It's a straight line. Am I correct? That's the best line you can do, okay? Because note that in our polynomial equation, you know that for t polynomial, it is just a naught plus a1 x. And this is a linear line, right? Because this is just like your y equal to mx plus c. So there are 2 unknowns, which means it requires 2 information. So in this case, our 2 information are the 2 points, So a0 and a1 can be found because we know this point values and this point values. So in our case now, using interpolation, okay, instead of using the actual curve here, which we do not know, we just use the interpolation. So this is our calculated value. And take note that this is the actual value, the true value, and this is estimated value, and this is our error. This is our error. Okay, so this is the idea uh, behind interpolation. So if you look at this, so this is basically similar triangle, right? So this is triangle 1, this is triangle number 2. So by using ratio, you know this value here, right? Because you already know this value, okay? You can find this value. So this is, if you read your textbook, this is basically similar triangles. So you can find the value. I think you have done this a lot of times, yeah? A lot of times. So I think the simplest one is just to find what is y equal to mx plus c, right? So once you know what is m and you know what is c, you can just plug in your x value to find your y. That's it. So you need to find the slope. So in this case, what is the slope? The slope is just this value minus this value. Uh, let me, okay, let me use my calculator here. Maybe let's use Excel here, much quicker, much quicker. Where is my Excel? Huh. Okay, so sorry, a little bit slow here. Uh, I have vision problem. If you, I don't know if you can clearly see from the camera, my right, my right eyes is very, very red. So my vision is blurry on one side. Not blurry, foggy. Ada kabus dekat dalam mata. Okay, so what we are going to do here is, this is our x. This is our log x, log of x. Okay, let me share my screen first. Okay, so let me zoom in. Okay. So let's redo this. Okay, so this is from the table, 8, 9, 11, and 12. So our question is what is 10? So I think we can use this. We can use these two value for linear uh, interpolation. So let's try to do the linear interpolation. So, and we know that our true value is this, right? So true value is equal to log 10 of 10. Oh, sorry, log 10 of this value here. Dollar. So true value is 1. Okay, true value is 1. So now let's try to do this linear interpolation first. So linear interpolation is this one. It keep giving me messages here. Oh, okay. I know what is wrong here because I'm copying this value. I'm not copying the formula. Okay, so this is from our table, 9 and 11. So what we need here is what I'm going to show you here is what we call Newton divided difference. Newton divided difference. Okay, I think you can check your textbook. What is Newton divided difference? So what we can do here is, first of all, we need to find the slope, right? Because it is this equation, right? Y equal to mx plus c, or for linear regression, linear interpolation, we need a naught plus a1 x. So we need to find what is a1 x and a naught. So the simplest way of this is just slope is just this value minus this value divide by value. Oops, wrong. This value minus this value. Right? So this is the slope. This is the slope. So next thing is, what is our C here? What is our C? What is our intercept? Okay, note that if we shifted our axis, okay, let's say this is our 9, this is our 11. Okay, let's say this is, what value is log 9? 0 0.95, 0 0.954 something, and 11 is 1.041, and this is the straight line. So can we find the slope? So the slope is just this minus this over this minus this, delta y over delta x. So which is this value here, and so, and the intercept here at our x-axis is this 0.954. So we can see that our value now, our a1x, a1x is 0.04357. Okay, x plus 0.954. Okay, so this is the equation here. This is the equation. So let me uh, uh, double check that. Hopefully this is correct. Hopefully this is correct. Cannot see. Okay, so okay, let's continue this. So if you look at your textbook, where's my textbook? I think I had here just now. Okay, so if you look at your textbook on Newton divided difference, I think this is chapter 17. Sorry, chapter 18. Okay, chapter 18. The way we write your Newton divided difference is this way. So the way you write is, I think this is, okay, I think this is slightly wrong because I need to shift. Remember that I shift my x-axis starting with 9. So I need to do this thing here. Okay, remember that from math, my x-axis did not start from 0. It started with +9. So what I need to do is to shift my axis. Okay, the slope is correct. The slope, if this thing is a straight line, wherever the location is, my slope is still correct. But my x-axis shifted from 0 and 0 to 9. Okay, because this is my new origin here. This is my new origin. Plus, my intercept is this value here, 0.954. So for Newton divided difference, the formula for linear, note that this is linear, first order, is just fx naught, which is the first value. In this case, this is my x naught, this is my x1, this is my fx naught, this is my fx1. Okay, so plus fx1 minus fx naught, x1 minus x naught. What is this? This is change in y divided by change in x. This is basically your a1 times x, which is the unknown, minus our shift in axis. This is our first point, right? So 9. So this is your a naught and a1. So this is the formula. But if you use this in Excel, you can see this is very simple. Look at this. So I have my a naught here. This is my a naught. This is my a1. Okay, that's my a naught. Sorry. Yes, this is my a naught, my intercept. This is my a1. But note that it shifted in axis. So instead of 0 and 0 here, it is not 0 and 0 anymore, but it is 9 and 0.954. But the slope will be the same anyway. Okay, so now if you look at this, if you use this formula, so what is my new uh, uh, value of log 10? Sorry, my estimated value of log 10. So in this case, this is just equal to a naught, okay, plus the slope, which is this one, times the shift. Oh, sorry, not this is plus, plus this, which is the slope, times the shift. So what is our x? Our x is this value, 10, that we want to find. So this is dollar and dollar minus our first point of the axis, which is 9, the shift. And my answer is 0.0997. Okay. If you are very familiar with the common method that you use, you can get the same. You can get the same answer. So let's look at the error here. Let's look at the error. So the error here is just the true value, the absolute value. So I'm not taking the sign here. Absolute value of true value minus estimated value divide by the true value times 100%, which is 0.21, about 0.22%. So let me B8 D11. Okay, so B8 is our true value. So let's do this. Just all right. So this is the error. This is the error. So look like because we do not know the actual point, so we just interpolate, and this is what we get: 0.997 instead of 1. So this is Newton divided difference. So if you look at the question, it asks for the second thing, linear interpolation using data at x equal to 9 and 11. What is the true percent relative error? So this is what we get. This is the estimated value. This is the error. This is the true percent relative error. Now, okay, so linear interpolation, you can use whatever you want. But for the part B, second order Newton interpolating polynomial using 3 data at 9, 8, 9, and 11. What is the true percent relative error? So let's do the same thing again. So now, what I'm going to do here is I just want to copy this. Okay, sorry, let's do this. Let's do this. Note that for second order or quadratic, okay, we have a naught. So quadratic equation is polynomial of the second order. We have a naught plus a1x plus a2x square, right? So we have a naught, a1, and a2. Okay, never mind. So what we have is only a0 and a1 because we are taking the data from the linear, because we are only using 2 points. Now, in the question says that we need to use 8, 9, and 10. Okay, so we can just copy this. Oh, sorry, not 10, 11. 10 is unknown. Okay, so 11, 8, 9, and 11. So now, the problem here is, because this is a quadratic equation, we need to have a 2 here. We need to have a2. So, how do we find a2 here? Oh, sorry, no, this is not a2. Because for this is the standard polynomial equation, but for Newton divided difference, Okay, we need to change the notation here. F to x is a naught plus, sorry, not a naught. I think in your textbook it's used, I think the letter B, the letter B. B naught, B1, x minus x naught plus B2, x minus x naught, x minus x1. Note that these are basically the same equation, but written in a different form. For example, a2 x squared, right? But this one is x times x. Again, this is x squared. So this is just algebraic manipulation, because for easy calculation, I think Newton manipulated the equation. So let me change this. Instead of a naught, let's use b naught to make this conform with the notation in the textbook. So this is b naught, b1, and b2. Okay, so now we have b naught and b1. Okay, because this is just the slope. So again, so to find, we can use the same thing. We can find the slope of these 2 points here using the same equation as before, which is again the same thing as this minus this divide by this minus this. Okay, so if I just copy this formula, it should be the same, because it's just the slope. So now how can we find b2 here? So b2 is just the slope of the slope, which is this, minus this, divide by the range is from, because this slope is calculated from this point, right? So the whole range is from this minus this, right? So this is the B2. Okay, so now what is the approximation here? So again, this is just this equal to B naught, which is this, times B1, oh, not times, sorry, plus, plus B1 times x. X is just our A4, which is that value, minus x naught, which is this one, okay? And then plus B2 times A4 here, this one here, which is 10, minus this times 10 minus this. Okay, now it has a better estimates, right? 1.0003. And what is the error here? So let me just copy the formula from here, and this is the error. This is the error. Okay, so take a look that when we use linear, our error is 10 to the minus 1, right? 10 to the minus 1. Okay, about 10 to the minus 1. when we use quadratic, which means we increase one polynomial order, note that our error is reduced to 10 to the minus 2. So from here to here, it reduced by 10 times, okay? Or one order of magnitude. Is it one order? Yes, this reduced by one order of magnitude. Okay, now let's redo this. Let's redo this uh, with same quadratic, but different, with different values. Now, instead of 8, 9, 10, why don't we choose 9, 11, and 12? Okay, and let's redo this calculation. Okay, let's just copy the whole thing here. See, look at the error here. Look at the error. Okay, both are quadratic, and again, the error are in the same order of magnitude. Basically, 10 to the minus 2 for the first one, and 10 to the minus 2 for the second one. But for linear, this is 10 to the minus 1. So as we increase the order of the polynomial that we use, the better is the error. Okay, the error become lesser. So what do you think if we use cubic? What happened if we use cubic interpolation? Okay, let's try to do that. Let's copy this. Okay, let's copy this and see what happened. Let's say this is cubic. Okay, I think the question asked for cubic, right? So third order Newton interpolation using 4 data. What is the true percent relative error? So now what we use is, what we are going to use here is 8, 9, 11, and 12. 8, 9, 11, and 12. Okay, so note that because this is cubic, there are 4 data points, which means we have one more parameter, which is B3. So we already know B0, B1, B2, and we need to find B3. So you see that from quadratic to cubic, B0, B1, B2, they are the same, no change. And let's calculate this one. So again, we need to calculate the slope between 0.11 and 0.12. So this is just the same thing, just copy this. And again, we need to find this. So this is just basically the change of this to this divided by this to this. This one, sorry. This one and this one means this point is calculated up to 12. So we can just, this is, okay, let's see, this is up to 11. So this one should be up to 12. Okay. And B3 is just the change of slope for this one. So this is equal to this. Oh, sorry. This minus this divide by this. Oh, divide by this minus this. Okay. So that's our B3. That's our B3. Okay, so again, the equation is for F3, okay, cubic, cubic is B naught, still the same one, B1, x minus x naught plus B2, x minus x naught, x minus x1 plus B3, x minus x naught, x minus x1 times x minus x2. Note that this is x times x times x. That's what makes it a cubic polynomial. So let me just use this because this is up to this point here, up to this point, right? So we need to add this thing here. So let me just copy this. Okay, this is the beauty of using Excel. So we do not need to repeat. Oh, what happened here? I think it should be Control C here and Control V. Okay, note that I need to plus with this. Okay, am I correct here? So, okay, this is first B naught, B1, B2, and now it should be B3 here times 10, which is A4, okay, which is 10 minus this times 10 minus x1. Okay, let me copy this first. Times x minus x2, and that's it. Okay, note this is now 1.000044924. And what is the error? So let's copy the error and see. Note again, we increase one order of polynomial. At the same time, we reduce the error by one order of magnitude. So this is 10 minus 1. This is 10 to the minus 2. Now this is 10 to the minus 3. So as the order of the polynomial getting higher, the error getting lesser and lesser. Okay, so that's the idea behind interpolation. Note that in interpolation, I hope you notice that we have 4 points here, right? And when we use all the 4 points that we have, okay, that's the only possible data point that we have. So the error become lesser, which means our approximation become much better instead of using only linear interpolation. Okay, that is the advantage. But if you look at regression here, for example, we have 1, 2, 3, 4, 5 points. Why are not we using fourth order polynomial? Okay, so remember in your test, don't get confused. Don't get confused. You need to know when to use regression and when to use interpolation. So the first thing that you should notice is that for regression, we are trying to fit our data to a model. And note in our class, we only covered linear and quadratic regression only. Okay, linear and quadratic regression. Okay, so even though we have, in this case, 5 data points, we are only using a second order because, in this case, uh, a linear regression. Why? Because this is correspond to A0 and A1. This correspond to A0 and A1, right? So in this case, this is a linear regression because to find A0 and A1, we can use linear regression. Okay, even though there are 5 data points. But in this case, okay, one more thing, note that these are data from experiment, which is bound to have errors, bound to have errors. So we are trying to minimize the error. So for example, let's say we have these are our data points. So what's the best fit for this line? Is it this or is it this or is it this? Okay, we know that it's going to be a straight line, but which straight line? Okay, that is why we have to minimize the error. In this case, in the regression, we keep talking about the SR, which is the sum of the residual square. Okay, so this is the uh, that is the regression, but this is interpolation. So interpolation means, in this case, all these values come either from a function which is a known a known function which has no error, or maybe your standard handbook, okay, and so on. So this value has no error, so we do not need to minimize the error because there's no error. There's no errors. So in this case, the more data point that we use, the better is the approximation. I think we have proven that using our log function. Okay, so log of 10 is the true value is 1, but when we use our interpolation function, cubic interpolation, you see that this is a close value to the true value, and the error is 10 to the minus 3, which is the smallest of all these uh, interpolation. This is linear, this is quadratic, this is cubic. This is cubic. All right, so we are done with A, B, C. Now let's try with Lagrange polynomial. So what is Lagrange polynomial? I think if you have taken, I think you guys are from BPI, right? Most of you are from BPI. So BPI do not need to take finite element. But I think something is, I think lately ni, I think you should take lah because finite element is becoming mainstream sekarang ni. Okay, so now let's look at the, part D. We have not done part D yet. Okay, part D is Lagrange polynomial. Okay, so what we are trying to do is to see which one is a better interpolation method. Is it Lagrange or is it Newton? Okay, Newton interpolating polynomial is also known Newton divided difference. You can take a look out at your textbook. Yeah. So for Lagrange, we can, okay, so Lagrange is another form of polynomial. Remember that we have, this is the standard form, this is the Newton divided different forms, and now we have one more, which is the Lagrange. Lagrange interpolating polynomial, which has the form of Fn x equal to the summation of Li x f x I. So this is basically just summation of Okay, L1 X F X1 plus L2 time X F X2 and so on. Okay, so for linear Lagrange, sorry my eyes is killing me macam nak tercabut biji mata. It's causing discomfort to me. Okay, so for the first order or linear Lagrange interpolation function is just f1 equal to L. Sorry, I think this one should start from I equal to naught, and so this is L naught, L naught. This should be X naught. Okay. 1 and X1. So this one is just L naught Fx naught plus L1 Fx1. So L naught is just X minus X1 over X naught minus X1 times Fx naught plus, okay, plus X minus X naught X1 minus X naught Fx1. Okay, the details are in your textbook. The details are in your textbook. Note that this is first order, and there's only X here. There's only X here. So both of these terms are first order. So they are just first order. Okay, so let's try to do the same thing. Let's try to do the same thing with the same equation. The same data using Lagrange polynomial. So let's rename this. Sorry sakit mata ni susah sikit lah. So let's just copy all this. So I'm using this same data, bit different method. Hopefully we get the same result. Hopefully we get the same result. Okay, so how do we do this now? How do we do this? So note that we need to find what is L naught and what is L1. What is L naught? Because we already know what is Fx naught. So in this case, let's try to use 9 and 10 kan? 9 and 11. 9 and 11. So let's copy this. Oh, before that, I think I have my something ready. Where is my, I think I have written somewhere. Uh, Oh, I have closed that thing. So we are going to use this formula here. We are going to use this formula, okay, to calculate, because we know our x1, we know our x0, x1, and we also know our fx0. Okay, fx1 is known. So for example, in this case, okay, so this is our x, this is our fx, fx naught, fx1. So we need to calculate what is our L naught and our L1. L naught is just this one. L naught is this value here, x minus x1. So this is equal to this value, minus x1, which is x naught. This is x1 divide by x naught minus x1. Okay, 0.5. And the same thing for L1, which is now just x minus x naught, which is $A$4 minus x1, which is this one. Oh, sorry, x naught divide by x1 minus x naught. Okay, so this is the formula, yeah? This is the formula. Okay, let me do something here so that I can, okay, let's can we take a 5-minute break because I need to I need to I need to take a minute, can we take a break for a while? 5 minutes, we'll be back around, I'll be back around, what time is it now? Okay, can we get back at 9:45, 9:45, right? 9:45. Okay, everyone, I'm back. All right, so are you guys ready? Dah boleh sambung?
Yes, doctor.
Okay, so I have put some formulas. Okay, so let me share you my screen here, my Excel screen. Where is it? Here, share content. Okay. All right, so this is the screen here. See that this is the formula. So x minus x1, x0 minus x1 is L0, which is this one. X minus x0, x1 minus x0 is this one, L1. So now what we need to do is L0 times fx0, which is this number here, right? So this time this. So we can do that equal to this times this. Okay? And L1 is this times fx1, which is the same thing, just copy this. And the sum, then we sum is 2, and we get 0.997817. And let's compare it with Newton divided difference. Are they the same value? Okay, they are the same value, right? Because for your information, let's see the error. For your information, Lagrange interpolating polynomial is derived from Newton divided difference. So they should get the same value. They should get the same value. So this is what I get. This is what I get, yeah? This is what I get. And the values are the same, The value are the same. So this is linear regression. Sorry, not linear regression, linear interpolation, Linear interpolation. So if you use your normal linear interpolation, you should get the same value as this one because they are the same thing, right? So this is the, now let's look at quadratic. Note that quadratic because it is a second order, right? So x times x, this is already x squared, x times x, x squared, x times x, x squared. So these are all second order terms. Second order plus second order plus second order. So the result is also second order. So L naught is just, again, x minus x1. Unfortunately, I cannot just copy this because there are different terms here. There are different terms. So I need to, I can copy this, but I need to put extra. Let's do this if I can. Okay, if I can, let's just copy this. So I think I should copy this C and Control V. Okay, now I need to put two brackets here. And then times x minus x2 x minus x2, x0, x1, and x2. Okay, divide by x0 minus x1. This one is already x0 minus x1. This must be another bracket here. Okay, x0 minus x2. x0 minus x2. Oh, yes, put. Okay, so there's a lot. Am I missing? I think this is one. Okay, be very careful with your brackets, Be very careful with your bracket. So the same thing, if you do the same thing over and over, I think we are running out of time. What time is it now? I think my clock is behind and my watch is okay. So let me just show you the same thing over and over. I think I have a solution ready here. Okay. So this is quadratic. Note that this is my linear and this is the error. And if we compare that with Newton divided difference, they are the same. Let's look at quadratic 8, 9, 11. It's a second order. It's a second order, 3 points. It's a second order, which means we need for Newton divided difference, we have B0, B1, and B2, second order. But for Lagrange, I think this is wrong. This should be L0. L0, L1, and L2, which is the first order. Second order, sorry. This is L1 and L2. So this one should be L0 and L1. So L1, the highest order is 1, which is linear. L2, which means the highest order is second order, which is quadratic. Okay, and if we do the same thing here, see that this is 1.003. Again, first of all, you notice that this is 10 to the minus 1. This is 10 to the minus 2. Error. This is error in the range of 10 to minus 1. This is in the range of 10 minus 2. And this is 10 to minus 2. What happens is that we increase the order from linear to quadratic. First order to second order. And we reduce the error from 10 to the minus 1 to 10 to the minus 2. Okay, and again, this is the same one as the Newton divided difference, 0.034. 0.034. Okay, 0.025 for this. Again, this is 0.025. Now with cubic, note that with cubic, the highest order is again third order. So this is L to the L3, which is Lagrange coefficient, okay, 3. And this is third order. Note that the error is 10 to the minus 3, the same one as Newton divided difference. So I don't know which one do you feel is much easier to calculate? Okay, which is easier to calculate? Note that in this case, you need to recalculate your L1 and L2 because when we change order, our L0 keep changing. Our L0 keep changing. Tak sama. Tak sama. From linear, L0 is 0.5, quadratic, L0 is minus 0.33, and cubic is minus 0.1667. But for Newton divided difference, you notice that our B0 remain the same. Okay, remain the same. Sorry. Our B0. Did I say B0? Yes, our B0 remain the same. Note that our X0 is 9. X0 is 9. In this case is 8. They are the same if they are using the same X0. For example, B0 is 0.95 if our X0 is 0.9. The same thing here. Okay, the same thing here. And if we are using 0.8, if we are using X0 as 0.8 as our X0, then look at our B0 here. Our B0 is the same. Okay, B0 is the same, B1 is the same, B2 is the same. Then we just add one more, which is B3. But for Lagrange, the problem here is, even though we are using the same X0, note that our this one, even though we are using the same X0, look at our L0. Okay, look at our L0. They are not the same. So this is one of the disadvantage of using Lagrange. But with Newton divided difference, we can just top up. We can just top up. We have more data, we just top up. We do not need to recalculate because with Newton divided difference, our where is it? This one. If our x naught is the same, our b naught will be the same. Okay, our b naught will be the same. Our b1 will be the same. But we need to add one more if we increase the order from linear to quadratic. This is x naught equal to 8. Note that our b naught, b1, b2 are the same if the order is also cubic. B naught, b1, and b2. And we add one more b3 because we increase the order from quadratic to cubic. Okay, so I think that's it for now. I think I see you again on Wednesday. Hopefully I can still work on Wednesday because I need to see my eye doctor on Tuesday. Kalau dia bagi saya MC, then I try my best to join class juga lah. Alright, so until next time, thank you very much. Alright.
Thank you, Doctor.